So what about the nucleus? So we had the electron, and we also had this idea there was something positively charged going on there. And of course, in that experiment, that was H+. But what about the nucleus? So Rutherford is credited with the discovery of the nucleus. So this was a little later. And he had been studying radioactive material. And his good friend, Marie Curie from France, would often send him interesting samples for him to study. I'm not sure quite how they got from France to England. Some of these were really cancer-causing things. I don't know how many people touched them without safety precautions on the way. But anyway, it's interesting to note that Rutherford actually did not die of cancer despite this research. He was literally the victim of his own success. So after his great discovery of the nucleus, which I'll tell you about, he became a knight. And at one point, he became sick, and he needed a doctor. Well, if you're a knight in England, you can't just have any old doctor treat you. You need to have a doctor that is also a knight. And so while he was waiting for a doctor of the appropriate ranking to come and treat him, he died. So he literally died of his own success. He was a victim of his own success. But it wasn't just his success, as I'll tell you about. He had some help. He had a really good graduate student, a really good undergraduate student helping him out. So he was studying these alpha particles that were being emitted from this radioactive material. And we know now that this is helium plus 2 ions, but that was not known at the time. They just knew something was coming out of this radioactive material. And they wanted to find out what it was and characterize the properties of this. So he had a postdoc named Hans Geiger. And this is the Geiger of the Geiger counter. And he also had an undergraduate student, E. Marsden. And so together they did the following experiment. And I wasn't, obviously there, but I'm imagining that by they did the following experiment, it meant the undergraduate and the graduate student, or maybe even just the undergraduate. OK, so here was the experiment. They had their radioactive material, alpha particles were coming off, and they had built a detector that would count how many alpha particles were coming off. And so they did the experiment, and they counted. And they found there were a lot of particles, 132,000 alpha particles per minute, in fact. So then they said, OK, let's see what happens if we put a piece of foil in the path of the alpha particles. And we're going to have really, really thin gold foil. So this is like smaller than a human hair. This is really, really thin foil. And they shot alpha particles at it. And they counted. And they got approximately, I don't know how many significant figures, but 132,000 alpha particles. Seemed to be, in terms of the significant figures, the same. So it was just going through. These alpha particles were just going through this thin gold foil. So they had this sort of vision then of the gold atoms being all empty space, and the alpha particles were just going through, no problem. But then they did one more experiment. And by then, I think this was the undergraduate. So they had built this detector, and they had built the detector so it could move. So they wanted, sometimes when you design something to do something, you actually want to use it for that. So if we have the alpha particles coming this way, and I'm the detector over here, and it had been sitting and I had been collecting it, the undergraduate was told, well, put the detector over there and see what happens. So the undergraduate moved the detector over here, and he said, you're going to see if the alpha particles hit the gold foil and backscatter. So we'll have the detector over here. So the undergraduate did this. They didn't think it was going to do anything. They needed something for the undergraduate to do. So they had him do that. And then they counted. And sure enough, click, click. It wasn't a lot, but there seemed to be some backscatter. About 20 counts, 20 alpha particles per minute. That was not expected. They were expecting 0. So they were detecting backscattering the alpha particles were bouncing off that thin gold foil and coming back at the move detector. So they could calculate this probability of backscattering, the count rate of the backscattering over the normal count of the particles. And so they had 20 backscattering events, or 20 counts, over the 132,000, 2 times minus, or 10 to the minus 4, or 0.02%. This is small, very small, but it was not 0. And I don't know how many times they did this experiment, but I can imagine there were lots of times they did the experiment that no one would really believe this result. And Rutherford himself said it was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So that's how he felt about it. He was like, I don't understand how this is working. This is so thin. It's like tissue paper, but yet these alpha particles are bouncing off something. So what did this all mean once they had repeated the experiment many times? So their interpretation then was that these gold atoms were in fact mostly empty. It seemed like all the alpha particles were just going through. Most of them were just passing through and not hitting anything. But there was something in there that could be hit. There was some concentrated mass in this volume that when the alpha particle hit that directly, it backscattered. And they later called this the nucleus. So they came up then with this new model, the Rutherford model, where you had mostly empty space, but you had concentrated mass inside that an alpha particle might hit and then backscatter. And Rutherford assumed that the electrons would be in that empty space and that this positive mass was going to be positively charged because he knew the overall atom was going to be neutral. So just a little nomenclature. We can think about the charge of the electrons in the atom as being equal to minus z to the e, where z is our atomic number and e is the absolute value of the electron's charge. And if this term is negative, then the charge on the nucleus is going to be positive, so we have positive z to the e, because overall the atom is going to be neutral. Then Rutherford went on to actually use this backscattering to measure the diameter of this positively charged, dense part of the atom, of the nucleus. And he was able to measure that diameter as a very small number, 10 to the minus 14th meters. So he did this with this backscattering experiment. So you might say, how can you get a diameter from this backscattering? And so that's what we're going to try right now ourselves. We're going to do an experiment. And Professor Sylvia Serra originally came up with the experiment to do in class. And so she built the first version of this gold foil right here. And it was originally she took something apart from her own research program. Since then, it's been replicated so that she doesn't have to shut down her research lab every year when we do this experiment in class. So here, imagine this as a piece of gold foil. And it's mostly empty space, but there are some small concentrated nuclei, gold nuclei, these styrofoam balls. And if we have, over here, some alpha particles, which we happen to have 502 alpha particles, if the alpha particle hits the concentrated part, it should backscatter. Otherwise, it should go through. So you are now going to be radioactive material. I don't know, is that the first time you've been called radioactive material? I'm not sure. But we're going to come around. Everyone can have one or two of these. So let me just tell you, you need to watch your ping pong ball Once you get it, you can move to the center, watch your ping pong ball. If it hits the edge of this, it's not a backscatter. Watch if it goes through or if it backscatters, and you will click in whether you had a backscatter event or not. And from that information, we will calculate the diameter of the nucleus. Do you want to put up the clicker?
A few more handouts.
I think everyone's good. Do we have any more? No, I think it's good. Okay, everyone, if you want to get up and get a better vantage point, do so, and let the experiment begin. I'm moving out of the way.
Boxes, whatever the box is. Over there. Can we throw them back at him?
Heavy ball after they've thrown it away.
Apparently it didn't take that long last time.
This will be a combo.
Okay. So go ahead and say whether you had 1, 2, or 0 backscatter events. And if your clicker isn't working, we'll ask you to raise your hand and tell us, especially if it was a backscatter event. Has everyone had a chance to click in?
What is it like screen?
Has everyone clicked in? You can't tell?
Can't tell right now.
All right.
Do you want me to count down?
Yeah. We're going to count down. Go ahead and click in, and then we're going to do the calculation. Okay. Display. Okay. Actually, we need to calculate the actual number of them, not the percent.
Oh.
Yeah.
You can switch that, but
All right. So we had some backscatter events. So let's see if we can use this information to actually calculate the diameter of the gold nuclei. All right. So we are going to talk about the probability of backscattering. So we have the probability is equal to the number of ping pong balls backscattered over the total number. And this will be related to the radius of those gold nuclei by the following. So we have the probability is going to be equal to the area of the nuclei, the total area, over the area of the whole atoms, so basically the piece of foil. And then that's going to be further equal to the number of nuclei times the area per nucleus. Again, over the area of all the atoms, or the piece of foil. Okay, so we know some of this information. So I'm going to move this up. Yeah, you have an actual number? Okay. 36 total. Oh, that's interesting. Okay, it's a lot of backscattering. Okay, so we can plug in some of these numbers now. So we have the probability is going to be equal. Someone counted, I didn't count, but someone counted that there were 120 nuclei. And the area is going to be pi r squared. And someone measured the entire frame, or the size of the piece of film, as 139,000 centimeters squared, or it was 1.39 meters squared. OK, so we'll assume that they counted the nuclei to 3 significant figures, that it's exactly 120. And we'll assume that they measured the box with 3 significant figures as well. OK, so now we can solve this for r, the radius, or for the diameter. So if we now solve for the radius, we'll bring the radius over, and we'll have the square root of the probability. And if we take these numbers, I did the math. I have a calculator if someone wants to check. 6.072 centimeters. And then the diameter is going to just be equal to twice that. So we have the square root of the probability times 12.14 centimeters. And now we need to calculate the probability. So the probability is going to be the number of backscattered, which was 36. 36 over 502. Someone want to have a calculator? Someone going to check my math? Check math for me. Check math, anybody? I don't have another prize, thank you. All right. Was it 26 or 36? I can't read up there. Double. Excellent. Checking math for me here.
Yeah, it's roughly 500.
OK. 26. And so what does this come out to be? What? 0.050. And now we need to plug that in. So we have d equals the square root of 0.050 times 12.14. And what does that come out to be? Point 2.71, and the actual was 2.5. Not bad. So using methods very similar to this, Rutherford was able to figure out what the diameter of the nucleus was. And this was a really important achievement of the time.